The effect of motion on a magnetic field. In a laboratory, a rectangular loop of wire surrounds the origin in the xz plane with extent h in the z direction and extent L in the x direction. So extent L in the x direction, extent h in the z direction, and y is perpendicular to the loop. The loop carries current I in the counterclockwise direction as viewed from the positive y-axis. A magnetic field bk hat is present, so it's on the z-axis. Part A, what is the magnetic dipole moment mu as seen in the frame S of the laboratory? Okay, magnetic dipole moment is the product of the area with the current, area defined by the current loop, and the direction of the moment is determined by the right-hand rule. So if we follow the direction of the current with our four fingers of the right hand, the thumb points in plus y direction. So we can see that a counterclockwise circulating current will produce a magnetic moment in plus y direction. So magnitude-wise, it's current times the area. So we can write this as a vector, magnetic moment vector mu is equal to the current the loop carries multiplied by the area in j hat direction. And since the area of the loop is the product of the height and length h times L, we can write the magnetic moment mu as I h L in j hat direction. The counterclockwise current determines the direction of mu. So the direction of the magnetic moment vector is determined by the right-hand rule. So we follow the direction of the current with all of the fingers of the right hand and the thumb points in the plus y direction. Let's move on to part B. What is the torque felt by the current loop? Now it has a magnetic moment and there's a magnetic field that's perpendicular to the magnetic moment. So this is going to create a torque. The magnetic field B has a magnitude B pointing in k hat direction. The torque the magnetic moment will feel is the cross product of the magnetic moment with the magnetic field mu cross B. So this will be IHL j hat cross with B in k hat direction. Now what is j hat cross k hat? Now using cyclic permutations here, I hat cross j hat is k hat, j hat cross k hat is I hat. And this is the positive direction. So from the cyclic permutations here, we can see j hat cross k hat is I hat. So the torque the magnetic moment will feel will be BIHL in I hat direction. So the torque is going to be in I hat direction. So mu cross B, using the right-hand rule, actually we can follow mu cross B. So our 5 fingers of the right hand point in the direction of mu curled towards B. The thumb points in plus I hat direction. So the torque is basically in the counterclockwise direction, looking at looking from the plus x direction point of view, and it's the vector points in plus I hat direction. Let's move on to part C. The same loop is viewed from a passing alien spaceship moving with velocity v I hat as seen from the laboratory. From the point of view of the aliens, the loop is length contracted in the direction of this motion. What is the magnetic dipole moment mu prime according to the aliens if their coordinate axes are aligned with those of the humans? The length of the loop is measured properly in the laboratory reference frame by the humans because the loop is stationary. The two endpoints are stationary with respect to the x-axis in this reference frame. So we can see that we can measure the length properly. But if we have a spaceship passing by on the x-axis, this length measurement will not be correct. It will be contracted, so it will not be the proper reference frame to measure the length. So length contraction occurs on the x-axis so if the passing spaceship measures the height h, they will measure the same thing as the humans, but the aliens will measure a different length due to length contraction. So L prime, the length that they will measure, will be the proper length L divided by the relativistic correction factor gamma. What is the relativistic correction factor gamma? It is 1 minus v square, the speed of the spaceship square, divided by speed of light square to the power minus 1 over 2. So the magnetic dipole measurement mu prime will give, instead of IHL divided by gamma in j hat direction, which will be the original magnetic moment measured in the laboratory reference frame divided by the relativistic correction factor gamma. Okay, let's move on to part D. The torque on the loop is the same when viewed from the laboratory frame and from the spaceship frame. Accordingly, the magnetic field must be frame dependent. What is the magnetic field B prime in the spaceship frame S prime? So if they are measuring the same torque, remember this torque is mu cross B. It is BIHL in I hat direction. Remember, BIHL in I hat direction. So this must be equal to the torque measured by the aliens, which is B prime IHL prime in I hat direction. So this tells me that B measured in the S frame multiplied by L is B prime measured in the S prime frame multiplied by L prime, which is B prime L divided by the relativistic correction factor gamma. So we find that the measured magnetic field by the aliens will be B times gamma in k hat direction. So the magnetic field will be frame dependent. Part E, if the electromagnetic field is EB is equal to 0B in an inertial frame S, then in another frame S prime moving at velocity v relative to S, what is the component of the magnetic field perpendicular to V? So we want to generalize this result. In part D, we have found that the magnetic field according to the aliens is the magnetic field according to humans multiplied by gamma. And in this setup here, the magnetic field B is perpendicular to the motion of the spaceship. All right. So we find that the magnetic field perpendicular to the motion of the spaceship is the perpendicular magnetic field in the proper reference frame multiplied by gamma. This is our result in general. Okay, so let's summarize what we did here. First, we calculated the magnetic dipole moment for a current carrying loop with area HL. It's the current it carries multiplied by the area and the direction determined by the right-hand rule to be plus j hat. The four fingers of the right hand curl in the direction of the current, the thumb points in j hat direction. Now, if there's a magnetic field in k hat direction, this is going to feel a torque because there's a 90-degree angle between the magnetic field and the magnetic dipole moment. Torque is mu cross B, IHL j hat cross with B, k hat, j hat cross k hat is I hat, so it's B IHL I hat. If there is a spaceship that moves along the x-axis with a relative speed v to the laboratory reference frame, the length which was properly measured in the S-frame will be contracted when measured from the alien reference frame. So by how much? It will be L divided by gamma, so that the magnetic dipole moment measured will change. It will be IHL prime j hat, or it's going to be mu measured in the laboratory reference frame divided by gamma. The current measured and the height measured perpendicular to the motion of the spaceship will not change. Now, they will measure the same torque. The two reference frames will measure the same torque. That implies the magnitude BIHL should be B prime IHL prime, which is L divided by gamma, telling us that the magnetic field measured by the aliens will be B times gamma in k hat direction. And in general, if the motion of the spaceship is perpendicular to the magnetic field, the component of the magnetic field measured perpendicular in the perpendicular direction is the perpendicular magnetic field multiplied by the relativistic correction factor gamma.